basic regression model we've seen so far assumes that the response is distributed according to a normal distribution, a Gaussian distribution. But for many practical purposes or our applications, this is really unreasonable. This is really far from reality. For instance, imagine cases in which the response is strictly a positive number. Say we're modeling the income of people, or perhaps it's ordinal, or like we're rating movies between 1 and 5, giving stars, 1 star, 2 star, etc. And the response is only 1, 2, 3, 4, or 5. That's it. Or what if the response is bounded? Let's say between 0 and 1. Say we're modeling the rate of unemployment in different countries. It's something between 0 and 1%. So what do we do in these cases? Well, there's something called the generalized linear model. And what we do is take those assumptions one step further. And with two particular additions to the general linear model, we are able to deal with these cases. Those two additions, those two components, are a specific distribution family for the response. So we are going to be able to assume something beyond just a normal distribution. We're going to assume something else like binomial or Poisson distribution. And what's more important, we are going to introduce this link function G. It's something that is going to transform the response in a certain way, and then we're going to build a linear model on the transformation of the response. Let me show you a little bit more. So the underlying model is still going to be a linear model, but instead of being a model of y, it's going to be a model of g of y. It's going to be a model of the transformation of y. And that's what we have here. We're really building a model of g of y. Or if you want to look at it the other way around, we have this inverse of g in the right-hand side. Either way, what we still have is a linear model. Underlying everything, we still have a linear model. It's only that we are transforming the response. And so for the basic case we've seen so far, just the general linear models we've seen so far, what do we have? Well, the distribution is, again, normal. We've been assuming a normal or Gaussian distribution. That's fine. And what about the link function? It's just the identity, what we call the identity link. This means that g of y is y. So in reality, we're still modeling y. There's no transformation, so to speak. But if we want to model something like a proportion, let's say that the response is bounded between 0 and 1, then we need to do something else. In these cases, what we select for the distribution is a binomial, and what we select for the link function, there's many different options, but normally what we do is use the logit function. So g of y is the logit. What is the logit? It's the log of the odds ratio. So it's the log of y over 1 minus y. What is this function doing? It's actually mapping the response, which is between 0 and 1, onto something that goes between negative infinity and positive infinity. So it's kind of stretching the variable y all through the real line. Let me show you. So the logit function is what we call a sigmoid. It's a sigmoid because it has a shape kind of like an S. And again, it maps the response, which is a probability between 0 and 1, onto something that spans the whole real line between negative infinity and positive infinity. And so this transformation looks like this. Here we have the original response, which goes between 0 and 1, and it's going to kind of stretch it such that it's going to span to negative infinity and positive infinity. So it's turning this number bounded between 0 and 1 into a real number without bounds. The inverse of the logit function does precisely the opposite. It takes something that goes between negative infinity and positive infinity, and it bounds it between 0 and 1. Right? So this is really what's happening. Instead of fitting a linear model on the response, which is bounded, what it's going to do is transform the response into something between negative infinity, positive infinity, and of that response, we're going to fit a linear model. So what's the difference? Well, something like this. Let's say that in this case, we are fitting data about the fraction of social houses in a neighborhood, and we are going to try and predict it through the house values in that neighborhood. So if we just fit a linear model that we've seen so far, we know it's going to look like a straight line, right? Something like this. But what's the problem? Well, first of all, for very low values in here, we're never going to be able to predict something close to 1. And it's going to give us negative predictions beyond almost 600. So we have a prediction of a value over here. It's going to be somewhere negative. And that prediction doesn't make any sense. There's no such thing as a negative fraction of social houses. Just like if we were able to go over there, it will give us something above 1, which doesn't make sense. So it's not really accounting for the bounds. We can have predictions that don't make any sense. If we do a logistic model, the one using a logit function for the transformation, then we have something like in the right. This is what we call logistic regression, because we are imposing this logistic transformation plus the binomial distribution on the response. So it looks something like this. And again, it looks kind of like an S or inverse S in this case. And what we see is that it's kind of smoothing or approaching towards 0 for very high values of the income, but it never really touches upon 0. It's always stretching more, and it would be stretching over here close to 1. So this is by design going to give us a response, a prediction, that is always going to be bounded between 0 and 1. So this is going to be a better model for this kind of data in which it doesn't make sense to go above 1 or below 0. This is by design. We don't have to care about the funny things to do with the predictions here in the linear model. This is by design into the logistic model. By the way, here's a major limitation of the regression curve in the logistic regression case, and that is that this S is symmetric. It's not, ideally the model should have been something like this. But that's another issue. Maybe we have to talk about transformations. Okay, so how do we build those models? Well, just the same way we've been building models so far. It's the same thing. How we specify the model, what factors there are, what interactions there are they numerical, categorical, etc. It's all the same, because again, underlying all this, we still have a linear model. How is the process of estimating parameters? It's all the same, only that instead of estimating on the response scale, we do it on the link space. We do it on the transformation of the response. It's all the same. So the linear model is still linear on the predictions. We can use numerical, categorical predictors, we can use interactions, transformations, everything we've done so far, we can still do it. So you see, this is a very, very useful exploration tool for a categorical response, for something that is 0, 1, a binary response, or a proportion. This is going to give us the full power of the linear model for the specific case of a bounded response. We can start looking into p-values, testing hypotheses, etc. Let's see more examples. So in this case, we have, again, the case of predicting the fraction of social houses in a neighborhood. And we are going to try and predict it only by the house value. So what we had earlier in the slides. We know that we're actually building a model of the logit, sure. And we have two coefficients, one for the intercept, one for the value, beta 1. And so, again, we know that we are fitting the model on the transformation of the response. So we're actually building the model here. So this response over here is really the logit of the social houses. And so you see it goes farther than 1 and below 0, no problem. This is what transformation is doing. And in here, you see, we're just fitting a linear model again. It's all the same. And so what we have here is this linear relationship between the house value and the logit of social houses. If we were able to transform this regression line again using the logit function, it would look into something like this. So this is what the regression line looks like when we're plotting against the response, the actual scale of the response between 0 and 1. So you see it's just transforming this blue regression line into something that looks like an S. In any case, again, we look into the coefficients. So in this case, we have a certain estimate for the intercept and a negative estimate for the value with corresponding standard errors, z-values, p-values, etc., etc. So again, we have just the part mathematic of the linear model and the part statistics about the linear model. And we can start complicating the models as much as we want. So in this case, we're going to have two main effects. We still keep the house value, but we're also going to include this categorical predictor, which models the degree of inconvenience caused by the neighbors. This is categorical. It's either low inconvenience or high inconvenience. Well, it's all the same. We know in this case we have one numerical predictor, one categorical predictor. So what we have is two regression lines, or the same regression line, but with two different intercepts. We have one line for one group, inconvenience low, and one line for another group, inconvenience high. And so what we have in the link space, again, is just a linear model. We have these two lines over here. We know they are parallel because we don't have an interaction. They just differ in the intercept, in the deviation from the reference point. And so again, when we transform into the response space, or when we plot the model in the response space, then they look like two S's. They are very similar to each other, very close to each other. They're a little bit different, but they never go below 0. They never go above 1. They're still giving us meaningful responses. And so what we have in this case, if we look into the regression table, is it doesn't seem, or there doesn't seem to be an effect of the degree of inconvenience. We have a very high p-value. And so we might be inclined to say, remove this term from the model because it looks like whether there's high inconvenience or low inconvenience, the fraction of social houses is not affected. And of course, we can have an interaction between the two. This is what beta 3 is doing in this case. So now, if we look into the link space, then we see two different slopes. That's what the interaction is doing, giving us two different slopes for the two groups. When we transform into the response space, it looks like this. Again, two kind of S-shaped lines or curves, but behaving quite differently. The red group, for example, in these low scores is much higher than the blue group, and they're getting closer over here for high values of the house value. We can still look into the regression table, and we find that both the main effect and the interaction effect looks like we don't have enough evidence to really say that these differences that we are modeling here are statistically significantly different from 0. And so we might be, again, inclined to remove beta 2 and beta 3 from the model, meaning we just stay with the model of social houses depending on the house value. So you see, we can do everything we've done so far, and we can start complicating this model more and more by introducing more and more predictors. In this link space, this is still going to be a linear model. It's everything we've seen so far, and we don't really have to care about how it looks like in the response. It's just a transformation that is going to ensure that everything remains between 0 and 1. That's it. So this is about fitting the model, about interpreting the coefficients from the model. What about predictions? Well, once we have fitted the model, of course, we can make a new prediction, just like in basic linear regression. But now we have two different spaces in which we can make a prediction. We can make it in the link space or in the response space. Normally, we're going to be interested in the response space. So we plug the numbers into the linear model, and we transform so that the prediction stays between 0 and 1. We are transforming back into the response space between 0 and 1. Why? Because, well, that's what makes sense to us. That's the nature of our response. That's where our observations live in the response space between 0 and 1. But many times we're going to be interested in making predictions in the link space. So without transforming back, still in the space between negative infinity, positive infinity, because that's what the linear model is actually living in. That's where the fitting process really happens. And if we want to inspect the model to see whether we should keep a certain term in the model or not, and how much does it really vary, then we want to make predictions and plot in the link space, because that's really where the underlying linear model is living in. And that's where, for us, it's going to be a lot easier to interpret the coefficients, because they're still lines. They're not S-shaped curves.